Good morning, everybody. How's my audio today? Can you hear me? Test 1, 2.
Oh, good.
All right, thank you. Okay. So before we get started, I'm going to post probably sometime later today. I'm going to post an assignment that's going to count as an exam number 3, I believe, and I need to get exam 2 probably graded for you guys. So look for that because I think we got this week, the end of the semester of May 4th, I think. So we're running out of time. So look for our assignment today. It'll be some problems to work and a little bit of research stuff I want you guys to do. Shouldn't be that big of a deal. I think that's it. I want to go back to a conversation we had in the last lecture. We talked about a couple ideas. We talked about a couple kind of oppositions. We talked about resistance and I mentioned to you that resistance exists in both AC and DC circuits. We talked about a concept called reactance. Reactance is AC only. And then we talked about impedance. Impedance is when you have a combination of resistance and reactance. And so we also mentioned that there were 2 types of reactance. There's reactance that you get, or the opposition you get from capacitors, that's called capacitive reactance. And then there's this device we'll talk about called an inductor. There's the opposition you get from an inductive reactance. And we talked about the symbols. We use R for resistance. We use X for reactance. And since we're talking about the reactance from a capacitor, we subscript this with a C. And if I have a combination of R and X, of resistors and capacitors, either in series or parallel, then I have impedance. And we use the symbol Z for impedance. I also mentioned that any kind of opposition, whether it's resistance, reactance, impedance, whether it's AC or DC, any kind of opposition, the unit would be ohms. The unit of measurement is ohms. So resistance has units of ohms, reactance ohms, and the combination R and X, impedance is ohms also. And so we talked about that. Now, how do these relate to each other? So to understand that, I introduced in the last lecture, we talked about an impedance triangle, which came from something called an impedance diagram. So I'm going to go back to that impedance diagram, just kind of as a review, and I want to start with the impedance diagram and then go back and explain where that impedance triangle came from for capacitors. And so I want to get rid of this. And please, I don't know if you guys are taking notes, but you want to write this down because this will make it a lot easier for you when you do the exam and homework stuff I'm going to give you. If you have everything right there, it's just easier if you have all the equations right there. All right. So don't worry about where this diagram comes from. Just kind of by definition, here's how it's set up. We start with this axis. And what you would call the x-axis or real axis, this is resistance. And then the y-axis is reactance. So if I have a number and I'm on this axis, that's all resistance. If I have a number and I'm on this axis, that's all reactance. Or if I'm down here, that's all reactance. Now we'll never be over here because my resistor value start up here at infinity and I can go down all the way down, maybe 10 ohms, 15 ohms. I can go all the way down to 0, but I can't get a negative resistance. So it's common to show this impedance diagram without the negative values for R because they don't exist. So why write them? So I can get rid of this. So usually when you see this impedance diagram, you'll just see the axis with the negative values for R cut off. The other thing to note is, as I said, if I'm here, that's all resistance. If I'm right here on this axis, that's all reactance. But what if I'm out here somewhere? If I'm out here, then I have a combination of R and over here, X. Well, if I'm out there, that's what we mean by impedance. Impedance means I have some resistance and some reactance mixed together. And so what I wanted to do is I gave you last time a set of equations for, I think we had a circuit like this, where I had a resistor and I had a capacitor. So we had R and we had XC. And I said, all right, well, if we want to calculate the total opposition, we wouldn't call it the total resistance because I got resistance and reactance mixed together. We call that impedance. Z total, you might think that you would add these up, but remember we said that these add up like a right triangle. So the way you would calculate this, and you can go back to the last video and review this if you want. We said that this is R squared plus XC squared square rooted. But when you report that impedance, you got to talk about the magnitude of the impedance, and there's also something called the impedance angle. And I use theta Z to denote the impedance angle. And the way you get that is just the inverse tangent of XC over R. But you want to make this negative. And I wanted to talk about why that value was negative. And in the last lecture, I kind of did it, but I went through it pretty quickly. So I want to go back and review that. So we're going to start with this impedance diagram. And I want to show you the name of the parts that's important that I want you to remember. And then we'll see how from the impedance diagram we get the impedance triangle for capacitors, and we'll do the same thing for inductors. So let me redraw my impedance diagram just so I can have a little bit more room. And the way it's drawn, again, I have my reactance axis. I'm just going to call this X. And I have my resistance axis. I'm going to call this R. So this whole axis right here, all these real numbers represent resistance from 0 all the way up to infinity. But on the reactance axis, from 0 up this way, going up, that is what we call inductive reactance, X. And for inductors, we use an L because we already use I for current, so they use an I to represent inductors. Now, we haven't talked about inductors yet. That's next. But we have talked about capacitors. So down here, these negative values, I won't go into, this is what we call XC. Those are all negative values. So if I have a circuit like this, I have a number. I think last time in the other video, I forget. I think I might have set this to maybe 3 ohms, and this might have been 4, or might have been reversed, something like that. So I had values like that. So if you had a circuit like that, I said, all right, calculate the total opposition. The total opposition would be, that's impedance, because I have a mixture of R and reactance. R and X is impedance. So what I would do is I would go over, let me put some tick marks here. So this means I'm going to go over 3 units on the R axis. So I'll come over here, 3 units. Put a dot right here. And then I'm going to go down, because XC, these are negative values. I'm going to go down 4 axes on the X axis, or XC axis. I'm going to go down, which will put me like right here. So I'm going to go down 4 units. So I'm going to put a dot right here. So anytime I'm on this axis, it's all resistance. Anytime I'm on this axis, it's all reactance, either capacitive reactance or inductive reactance. But anytime I'm out here in one of these quadrants right here, that's impedance. And since this dot is out here and not on the axis, that means that's impedance. Well, how do you get to that dot? Well, it's easy. We went over this way on the resistance axis, and we went down this way 4 units on the reactance axis. So I can go over and down to get to that point. That point right there, that dot represents impedance. So I can go over and then up or down. Or I can start right here and I can go right out to that point directly. That's where I get the triangle from that we talked about in the last lecture. So remember I said I'm going to draw the impedance triangle for the capacitor the wrong way. I drew it like this. And I said this is R, this was XC, and this is Z, and this is a right triangle. Well, here's my right angle right here. So when I said I'm drawing a right triangle the wrong way, you see it's actually flipped over. And I want to explain that negative sign. That negative sign is going to make this angle negative. When you put that in your calculator, if that negative sign weren't there, you took the inverse tangent of a positive number over a positive number, you get a positive angle, which would not be correct, because you can see over here, impedance, my angle is actually negative if I measure from here to there, which is what I want. So that's the origin of that negative sign. Now, it depends on how you want to write it. Usually when I write this equation, what I do personally, I go ahead and I put that negative sign in there. So I put it in there like this. Now when you square a negative number, it's going to be positive anyway. So you might say, well, a lot of students will say, well, I'm not going to put that negative sign in there because when I square it's going to be positive anyway. So why not just write it as x squared, which is true. But the problem is if you do that and you're working, you're under stress, you might forget that number is really negative. So if you write it as a positive, you might accidentally put a positive number down there, which is going to make that angle positive, which will give you the wrong answer. So I usually just stick that negative sign in there just so I remember to put it right there. But I want to explain where that negative sign came from and why the angle's negative. And when I said I was going to draw the triangle, I actually should draw the triangle like this. This is the triangle. Well, that's the right angle. This is R, because R is always positive because I'm coming over this way. But this part right here, that's XC. So what I do is I just use it like this, because most people think of the right triangles, they think about it this way. So it's okay to think about it this way as long as you remember when you get that impedance angle, then you got to stick that negative sign there, because you got to report the impedance, which here when we did this, we put these numbers in here and we got 5. So we got 5 ohms, but then there's a theta Z, which would have been negative, and I don't have a calculator, but it would have been negative, in this case, minus 3/4, whatever that came out to be. So just remember that when you do your calculations. So hopefully it makes sense. Now there's, let's see. Let me show you something else real quick. Anybody have any questions over what I did so far? Does it make sense? I just really went back and kind of reviewed some of the stuff we talked about in the last lecture, because I was kind of rushing. I wanted to make sure this was clear why this is negative. So does this make sense so far? Anybody have a question? Okay, I look over there because my computer's over there. So sometimes you guys can use your audio, your mics, but sometimes they type those messages and it pops up. So you see me looking over there. On camera, I watch myself on camera and it looks weird because I'm looking over there and it looks like I'm looking for something, but I'm actually looking at you guys on the computer to see if anybody sent a message. Well, let me show you something that's kind of interesting. let me see here. Suppose we put a voltage source on this. Let me redo the circuit. And I got to think about some numbers that are going to work out nicely. So I'm going to give you the same exact circuit because those numbers are easy to work with. You guys might want to get a calculator because we basically probably need to calculate that angle. So if you got a calculator, get it out. But let me give you an AC circuit, a simple circuit. And we'll keep those same values that we had before. And we'll just go through a calculation. So we've got a simple series circuit. And this is my XC, which we'll leave it at 4. And I think we have this at 3. Then I'm going to make this, let's make this 10 volts. Now, if I just say 10 volts, remember AC, it could be peak, it could be peak to peak, it could be RMS, it could be instantaneous. Well, anytime in the class, I just put a value up like that. If I don't tell you what it is, assume it's RMS. Most of the time you work with AC values, unless you're doing something in a like a lab situation, you're going to work with RMS. So remember, RMS and effective mean exactly the same thing. So let's say I had this and I want to do an analysis on it. And by analysis, I want to find the current in the circuit. I want to find the voltage drop across each component in the circuit. So how would you do that? And the answer is you do exactly what you would do if this were a DC circuit. The only thing you got to remember is when you're adding up total ohms, you just can't say, all right, my total opposition will be 3 and 4. It's going to be 7. That would be wrong because remember, they add like a right triangle. So let's just go through the steps and just kind of look at what we get if we get a complete analysis. And you guys, one of you guys, take your calculator out because I want to get that angle. We've been not calculating this, so let's get that angle. I had fried chicken and French fries for breakfast, so my stomach is like killing me. So I'm trying to drink this water. All right, isn't it crazy? So let's do an analysis, and I want to find current. I want to find voltage drops. I want to find total opposition. So in any DC circuit where you know all the values, they're all done the same way. I don't care if it's AC, DC, any kind of series circuit is what I should say. The first thing you're going to do is find the total opposition. The second thing you're going to do is use that total opposition and the voltage to get the current. And the third thing you're going to do is use the current to get the voltage drop across each component. So let's do that. Let's just walk through that. So the first thing to do is to find the total opposition, which, since this is an AC circuit, and I have resistive ohms and reactive ohms mixed up, that total opposition is called impedance. So I'm going to find Z. Now, we already found that before. Z is R squared plus X squared square rooted. So for Z, I'm going to get, we got 3 squared plus 4 squared. That's going to be, that's a 9, and that's a 16. That's going to give me a 25. This is going to give me the square root of 25, which is 5. So I know my total opposition, ZT, or just Z, I'm calling it Z, we'll call it Z. I know it's 5. It's 5. Well, the units will be ohms. But then I got to get that theta Z. I got to get the theta Z. And to get the theta Z is where you got to use that tangent. But remember, that 4 is really negative. Anytime you see a XC there, then just mentally supply that negative sign to put not here, you know. But you got to put it in that tangent equation. Now, when you get your calculator out, make sure your calculator is in degrees. On the exam, when I give it to you, if I give you a problem like this, don't make sure you're always in degrees. Just put it in degrees and leave it there. I have had occasions where a student will do the exam the right way, but they were in radians, and so I had to take credit away from them. So just do everything in degrees. You don't have to worry about it. So if I want to find theta z, I'm going to erase this so you can go back and look at the video. So theta z is going to be the inverse tangent of the x part, is xc, over r. And remember to put the negative sign there. So I got minus 4 over 3. And if somebody has a calculator, do the inverse, make sure you're in degrees, do the inverse tangent of minus 4 over 3 and tell me what you get.
I got negative 53.1.
Negative 53.1 degrees. So theta z, I'm going to put it over in the corner. I hate to be all over the board because I might need that. Theta z is minus 53.1 degrees. Okay, so make sure you can do that, and I'm sure you can. So now we found the total opposition. The next thing we want to do is get the current. Well, to get the current, if this were DC, to get current, I would take my total voltage and divide it by my total resistance. Well, in AC, the total, if I have a mixture of ohms, would not be R, would be Z. So that's all I got to do. So I got 10 volts divided by 5 ohms. Now, if we were in another class and we have more time, that's 5 ohms at that angle. But we're not gonna get into that. But this angle actually turns out to be important. If you ever heard of a vector, these are like vectors. They're called phasors. But what you guys do, that's a little beyond what we need to do for the course. So if you can just get theta z, I'll be happy. And then we'll just deal with the magnitudes for current and the rest of the stuff. But you can see right here, I'm going to get 2 amps. And that 2 amps, since this is in RMS, we assume this in RMS, then that 2 amps is in RMS. So we have current in the circuit of 2 amps. So let me put that on my actual diagram. 2 amps. All right. Now let's find the voltage drop across each component. That's my third step. So to find the voltage drop across each component, voltage drop for the resistor, it's just I times R. Voltage drop for the capacitor, it's just I times XC. If I take I times R, that's 2 amps times 3 ohms. And if I take I times XC, it's 2 amps times 4 ohms. I'm running out of marker. So if I do the math here, I get a 6 here, 6 volts, and I get 8 volts. So over here across the resistor, I got 6 volts from there to there. And now here I got 8 volts from there to there. Now, does anybody see anything wrong with our answer for our voltage drops? I'll give you a hint. Think about Kirchhoff's voltage law. Do you remember Kirchhoff's voltage law and what it says?
Yeah, the total voltages have to equal the source voltage.
Yeah, right? Last time I checked, 8 plus 6 did not equal 10. Right. So either Kirchhoff is wrong, which means his law has been broken, and you get a Kirchhoff ticket. Ha 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 ha. You guys are allowed to laugh at my corny jokes. Or we made a mistake here, or is there something else wrong? What else could be wrong here? Well, let me show you how to think about this. Let's go back to our impedance triangle. That's going to help us think about this the right way. So if I go back to my impedance triangle for this circuit, here's what I had. Now I'm not going to put the numbers in there. I know this is R. I know this is that's X, C, and that's Z. Now the thing about a triangle, it's like an equation. If you have an equation in algebra, a math equation, if you multiply both sides of the equation by the same thing, or if you divide both sides, as long as you do the same thing to both sides of the equation, you keep the equality between the two sides. Well, triangles are kind of the same way, only we got to deal with all three sides. So I can do whatever I want to this triangle and not change the angles. If I took the sine and cosine, as long as I do the same thing to each side. So if I want to subtract 2 from each side, I get a triangle that we say is similar. If I want to divide each side by the same number, it's the same triangle, just smaller, but these angles stay the same. What I want to do is multiply all sides by a number. As long as I multiply all three sides by the same number, I get a bigger triangle, but all the sides are proportional. I really don't change the triangle. And so what I'm going to do is multiply this side by I. I'm going to multiply this side by I. I'm going to multiply this side by I. Well, what is I times R? I times R is VR. VR is I times R. So what I get on this, by multiplying the bottom part of that resistor by current, I get the voltage of the resistor. I get VR. When I get by multiplying I by the capacitive reactance, I get the voltage across the capacitor. I get VC. And when I get by multiplying the current times the total opposition, I get VT. So what I've done here is I changed that impedance, that impedance triangle into a voltage triangle. And now what this shows us is how the total voltage is related to the voltage across each component. It's actually related like this. Since that's the right triangle, total voltage is not equal to the voltage across the resistor plus the voltage across the capacitor. It's actually equal to VR squared plus VC squared square rooted. That's Kirchhoff's voltage law when I have an AC circuit and I have reactance and resistance mixed together. That's how I can calculate the total voltage. So let's try it. Let's see if that actually works out since you got a calculator. What happens when you take 6 squared plus 8 squared and you take the square root of it? Did you get something that's close to 10? Yes or no? Anybody doing calculation? The question is, does this equal 10 volts?
Yeah, you get 10 volts.
You get 10 volts. So on the exam, when you do this kind of stuff, you got to remember, things add up. If I only had resistors, I just add them up. And I think somebody in your class asked this, if these were all capacitors, can you just add them up? If this was a 3 ohm capacitor and that was a 4 ohm, you would just add them up. I'd have 7 ohms. So as long as I'm adding the same thing, if I had all resistors, just add them up. All capacitors, just add them up. Even if I had all inductors, which we haven't talked about yet, just add them up. It's only when you have a resistor and another component, like a resistor and a inductor, or a resistor and a capacitor. It's only when you have resistance and reactance that you got to go to this right triangle stuff. And then Kirchhoff's Polish law adds up like a right triangle. So that's pretty important. Okay? So I think that's it. Did we do magnetism yet? Did we talk about magnetism already or not? I can't remember. Usually I talk about, because I want to talk about inductors, but what I do is I talk about magnetism first. And I can't remember if did we talk about magnetism or not? You guys don't remember if we talked about magnetism?
I've got some magnetism in my notes.
You do?
Yeah.
So we talked about flux and flux density and all of that?
Yeah, it looks like it.
Okay. All right. Well, what I want to do, because there's one more piece to the puzzle, and I don't know, what do you guys do for lab? I know Russ had you doing one you did a sine wave lab, didn't you? Did you do one on the sine wave already?
Yeah, we did that last week.
Okay. And so, I don't know if he's going to give you an RC lab. I want to talk about the other component that's missing, and it's called an inductor. And you know, we talked about capacitors, the way capacitors behave in DC circuits, and I could do the same thing for inductors. I'm not. We're going to skip over the inductors and the DC part of it because I don't think for what we want to do, I don't really think that's important. And capacitors are kind of cool because you can charge them up, you can store the charge, use it later on, you can work on timing devices. Inductors do have applications, but I think capacitors are a little bit more interesting to look at, probably a little bit more useful to you guys. So what I want to do is talk about the missing piece of the reactance opposition called inductive reactance. So I want to go talk about inductors, what they are, and then show you how that comes to play right here. Yeah, we got time. I think I started late. I had an appointment, so I set the time for what was it, 10:15, and I have it set to go off at I think I set it for 15. So I'm gonna go a little past our normal time. You have to sign out because you got something going on. That's fine. I'll put this will be up on YouTube, so you can always go back and look at this part. I had to shift the time a little bit, or if you have another class that starts up, I don't know if you guys have another lecture that starts up at 11. If you need to cut out of here, you can, and I'll make sure to get this up on YouTube tonight. So let me just briefly introduce the inductor. And we went into a lot of the physics behind capacitors. We looked at how they were made and how certain parameters like the area of the plates and the distance between plates and the dielectric constant, how that was all related. I'm not going to do that for inductors. An inductor really is just a piece of wire. That's all it is a piece of wire. But they usually coil the wire up, so it's a wire that they coil up like this. So the device, the coil, it's just a coil. And the device is called an inductor, and its property is called inductance. And the unit for inductance, well, they use L for the symbol. They use a C for capacitance. They use an L for inductance. And you know, for capacitance, the unit was the farad. Well, for an inductor, the unit is a Henry, capital H, like a person's name, Henry. So I might have L, and it might be 3 Henrys. Now, I know I mentioned, I'm not going to go into the physics, and we did some capacitors in series and parallel. And those are really easy because they behave just like resistors when you hook them up in parallel or series. So what I'm saying is, if I have 2 inductors, say I had I had two inductors. I got L1 and L2, and that's 6 Henries. If I wanted the total inductance, they got just like resistors, I would just add them up. So I got 6, I got 3. My total inductance would be 9 Henries. If I had those inductors the other way in parallel, they act just like resistors. If I hook them up like this, let's say I have 6 Henries, and I got it in parallel with 3 Henries, then whatever formula you would use for parallel resistors, you use the same for parallel inductors, just change the R's to L's. So you might use, you might say, all right, I know 1 over RT equals 1 over R1 plus 1 over R2. If those were resistors, we'll just change them all to L's. This would be L1, this would be L2, and that would be LT. So you really know the formula for this because you already know the formula for resistors. Now for these numbers, the easiest one to use, so you don't have to do a bunch of calculating, would be the product over the sum. So RT equals R1 times R2 over R1 plus R2. So I'll just change these all to L's. So it'll be L1 by L2 over L1 plus L2. And then you got it. So I got a 6, and I'm going to leave the units off. I got a 6 and a 3. I got a 6 plus a 3. I got an 18 on top, a 9. That's going to be 2. So it'll be 2 Henries will be my total. So inductors in series and parallel, just like resistors, no big deal. Again, I'm not going to ask anything about that on the exam, nothing, because that's just simple. But I really am interested in how they behave, how inductors behave in the AC circuit. How they behave in the AC circuit. Well, first thing to note is to go back to our impedance diagram and remember where the inductance exists. So on our impedance diagram, if I redraw it, you know that this is resistance. And this is reactance. If I'm in one of the quadrants, that's impedance. Well, what I mentioned before was this part right here on the bottom, those values represent XC. On the top, these values represent XL. So basically here, let me put that in another color. Here, in this, I have capacitors. And then here, that would be my inductor. And then here, that would be my resistance. So if I'm on this axis, is that. I'm on this axis. Don't confuse. This kind of looks like a coil. Let me make my coils look like a coil. Because it's easy to confuse the coil. These are more round like that. And these are sharper. So if I'm here, if I have R and XC, I got Z. If I'm here, I have R and XL, again, I got Z. If I'm only over here, I got reactance. So what happens if I have, let's say, capacitors and inductors in series in the circuit? What happens if I do that? Let's look at that. Well, it's actually pretty simple. I think somebody raised this point in your class last time. If I have an inductor and I have a capacitor, and let's just say this is, I don't know, let's say it's 15 ohms. Now that's an inductor, it's reactive, so it's X, but it's XL, because that's an inductor, and this is XC. And just to keep the math, we'll make this 10 ohms. Well, it's 10 ohms, but what you have to do is mentally supply. Remember the position of XC in our impedance diagram. The 10 is actually a negative 10. So if you want to put that in there, then my total reactance in this case is going to be 15 ohms minus 10 ohms. It's going to be actually 5 ohms if I have only X's in my equation. Well, what if I stuck an R in there though? What if I stuck a resistor in there? How does that change it? Maybe this is, I don't know, let's make it 20. Well then, if I want to find my total, I still need to do this to find XT, to find my total reactive ohms, but then this circuit reduces to this. Now, since that's positive, I'm going to draw that, or actually, you know what? Let's do it like this. I'm just going to draw my X as a box. So I got 20 ohms, but my XT here now is going to be 5. And that's a positive 5 because my inductor value is bigger than my capacitor value. And now you have exactly the circuit we had before. If I want to find my total Z, what I would do is, and I'm not going to do the math, but ZT would just be my 20 squared plus my 5 squared, square rooted, and my theta Z would just be my inverse tangent, 5 over 20. Now, I do not put a negative sign here for this one because that number is really positive. Here, my inductor value was bigger than my capacitor value. So when I combine those reactive ohms, this box represents this box right here. So when I get a total X, my total X in there is a positive 5. If I have reversed these and made this 15 and made that 10, then that would be negative, and then you got to worry about that negative being here again. Impedance cycle. Okay. One more thing, and then we'll call it a day. We'll sign off. And I want to do this. I don't know what Russ is going to give you for lab, or you may not even get to this. He might just cut it off after last week's lab, or may give you something for this week. I don't know what the plan is, but if he gives you this, I want you to at least have the numbers. How do we calculate XC? Well, if you go back to your notes and think about it, I gave you a formula for it. XC was equal to 1 over 2 pi FC. So you got to know the frequency and you got to know the capacitance. If I have capacitance, if I don't give you the ohms, I might tell you instead of this is 10 ohms, I might say, hey, this is that's 30 microfarads. If I gave that to you like that and I didn't give you the ohms, you got to convert that to ohms. And the only way to convert it to ohms, I would also have to give you the frequency. So you would have to put the 30 microfarads in there per C, and whatever the frequency is, I would have to give you that, and then you can calculate XC in ohms. Sometimes it's given that way. Well, what if I have that same situation with XL? What if I said this was, what if I said that was 1.5 millihenries? How would I convert that to ohms? Well, there's a formula just like this one that I want to give you, and you can put that in your notes. So if I'm given the inductance and I want to convert it to ohms, XL is 2 pi FL, and I'll just define these as what you think they are though, where again, F is frequency, this is the frequency, and this new thing right here, that's inductance. Now, I don't know, I may give you some of this just so you can calculate and see how it works, but we'll deal with this in ohms most of the time. So now you have enough information to do a complete series problem, no matter what element I have in it. If I have a circuit where I have all resistors, and it's AC, you just add them up. If I have all capacitors, and I know the ohms for the capacitor, so I got X C1 and X C2, again, you just add them up. If these were, if I gave you the C values, if I didn't give you the ohms, I gave this to you in farads, so if I gave you C1 and C2, then what you do is put these values in that equation and convert it to ohms. But to do that, I got to give you F. And the same thing with inductors. If I have all inductors, so I got L1 and L2, if I give you inductance, if I give you L, again, I got to give you the frequency, and you can convert these to ohms. So then you will use a formula and convert this to XL1 and XL2, and then you just add them up, just like resistors. You just add them up. It's only when you add a resistor and a reactive component together where you got to use the right triangle stuff. So now with what we talked about, and I know we got to practice it a little bit, so I'm aware of that, but now you should be able to have a problem like this. You got the problem maybe with a resistor, you got a capacitor, and you got an inductor. So I got R, I got XC, and I got XL. My expectation is you should be able to do a problem like that, and if I gave you a voltage across the network, you should be able to find the current, you should be able to find the voltage drop across each component, and you should be able to prove like Kirchhoff's voltage law, that kind of stuff. So this should be enough to get you through any lab that Russ may give you. We haven't done anything in parallel, but we can do that next time. So what I want to do next time is I'm going to just do a little bit more practice here. And then I'm going to look at the syllabus to make sure I've covered most of the topics and kind of hit. I think the last day is May 4th, but I think May 4th is a Monday. May 4th, I believe, is a Monday. So we got time to get through this, but I want to give you some other problems that I can count as an exam so that I don't want to give you anything too hard on the final. I'd rather just kind of break it up. So I'll give you some basic stuff, and you can just, take it easy, lay back, and look at your notes. You can, look at your book, look at whatever, and it'll be some stuff to work. I'll count as an exam grade. And then we'll talk about the final exam, which I plan to have on the last day of class. So plan on the next lecture that we'll do some more practice mathematical stuff with this. We'll do stuff in parallel, and then I'll let you know where we're going to move to next. Now, before I sign off, does anybody have any questions for me about this stuff or about anything else that relates to the class? Any questions? Okay, well, you guys have a great rest of the day. Stay safe, and I will put this video up sometime tonight. And if you have any questions, you know how to text me. You can text me or email me. I prefer a text. And just stay safe, and I will see you later.